Descriptive Astronomy, Lecture 19, The Milky Way, for Tuesday, April 7th, 2020, though it was actually released on Wednesday, April 8th. Sorry about that. Please take notes on this lecture. Pause the video and go get your notebook. I'll wait. Welcome to the fourth quarter of the semester. In the first quarter, we learned the fundamentals, what the sky looks like from Earth, the history of astronomy, and the physics of astronomy. In the second quarter, we learned about planets. The third quarter, stars. Now in the fourth quarter, we'll learn about the big stuff, galaxies, the structure of the universe, and the nature of space and time. Let's begin, as we usually do, with poetry. Say it with me. A low-mass star, like our sun, becomes a white dwarf when fusion is done. A high-mass star becomes a neutron star. The most massive souls become black holes. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. So we live in a galaxy of a few 100 billion stars, plus a bunch of gas, dust, and something we call dark matter, which we'll learn about later, all bound together by gravity and orbiting the galaxy's center of mass. So what does this galaxy look like? Well, that very much depends on where you look and what wavelength you're detecting. This image is an infrared image showing the dead center of our galaxy. The bright red areas are really just regions of warm gas, but you need a telescope with an infrared detector to view this image. Without a telescope, the Milky Way looks like this, a faint band of light that surrounds us. The bright parts here are the combined light of billions of very distant stars, while the smoky parts are dust that absorbs starlight, like smoke from a campfire. So why does the Milky Way surround us like that? Well, the Milky Way is shaped like a disk, and we're inside it. So imagine you're an ant standing on this plate. What does the edge of the plate look like to you? Well, it encircles you. It surrounds you, just like the Milky Way encircles and surrounds the Earth. Though to be clear, Earth is not the center of the galaxy. We're closer to the edge than the center. Our galaxy is full of dust and gas, which we call the interstellar medium. In places where the interstellar medium is both dense enough and cool enough, new stars are born. Here's an artist's conception of what the Milky Way would look like if we could send a probe outside the galaxy and look in from edge on. Remember, we can't send a probe outside the galaxy in real life. Our most distant probes have barely left the solar system, and there are a few 100 billion star systems in the galaxy with lots of space in between. So we can't send a probe out of the galaxy. We take measurements from Earth and compare our measurements to images of other galaxies to gain insight into the shape of the Milky Way. There is a bulge at the center with an older star population and not much dust and gas. In the disk, on the other hand, there are both old and young stars, because new stars are still being formed in the disk, because that's where most of the dust and gas is. Beyond the disk is the halo, where we find globular clusters. There, right there, right there, right there. These are densely packed balls of a few 100,000 stars each that are as old as the galaxy itself. The disk is about 100,000 light years in diameter, and our sun, right there, is about 27,000 light years from the Galactic Center. So now, let's move our imaginary space probe so that we can see the disk. We have really good measurements of our local neighborhood, which is right there. But the far side of the galaxy over here is obscured from view by dust, gas, and stars. So the part of the map near our sun, right there, is based on measurements, while the opposite side of the galaxy is based partly on measurements and partly on the assumption that the galaxy is symmetric. That is, that the far side looks more or less like the near side. And many galaxies are symmetric, though some are not. The bulge here in the middle is elongated, so we call it a bar. The Milky Way is therefore classified as a barred spiral galaxy. There are two major spiral arms, one here and one here. We live with several smaller arms then that spur off the major arms. We live in a spur right here called the Orion spur, which shoots out of the Perseus arm. Stars in our galaxy orbit the center of the Milky Way. Stars in the disk all orbit in more or less the same direction in the disk. All forward prograde motion, as they call it, all the same direction. Although they do bob up and down, first above the disk and then below it. Remember that objectively there is no up or down in space. So when I say above the disk, I mean away from it. And when I say below the disk, I mean away from it in the other direction. The gravity of the stars in the disk is always pulling the stars toward the disk. So if a star happens to be above the disk, it gets pulled back toward it. But the galaxy has no floor, so the star passes through the disk, and now it's below it. So then gravity pulls the star back up, and it goes right up again through the disk. Now it's above the disk, being pulled downward, then below it being pulled upward, and so on, down, up, up, down, up, and so on. So the disk stars, including our sun, bob up and down as they orbit because they're being pulled back to the disk, always back to the disk, by the gravity of the stars in the disk. Oops. Bulge stars here and halo stars, globular clusters, do not orbit in the plane of the disk in general. Their orbits have random orientations. Some orbit 30 degrees from the disk, some will orbit 90 degrees from the disk, and some orbit backward. So the stars that orbit in the bulge, the stars in the bulge orbit in random orientations. And that's why the bulge is so much thicker than the disk. The stars orbit the bulge in random orientations like billions of moths buzzing around a lamp. So here's a thought question that just might end up on exam 4. Why do orbits of disk stars bob up and down? Are they stuck to the interstellar medium? Does the gravity of the disk star pull them toward the disk? Or do halo stars knock them back into the disk? Write the answer in your notebook. Yeah, I think you got that. The gravity of the disk is always pulling stars toward the disk. So if a star moves a little bit out of the plane of the disk, it gets pulled back toward it. So we measure the mass of a star by watching planets orbit the star, or by watching the star co-orbit a binary companion. Likewise, the sun's orbit around the Milky Way tells us the mass of the Milky Way, or at least the mass of everything inside the sun's orbit, from the center out to the sun's orbit. It takes 230 million years for the sun to orbit the galaxy, meaning the total mass encircled by the sun's orbit is about 10 to the 11th solar masses. That is about 100 billion times the mass of our sun, and that number comes right from Newton's law of gravity combined with Newton's laws of motion. Alternatively, you could use the law of conservation of energy to compute that mass, but that's a little beyond the scope of math that we've seen in this course. So our galaxy consists of a bulge, a disk, and a halo. Stars in the bulge and halo orbit with random orientations, while the disk stars orbit in more or less the same direction, except they do bob up and down a little bit. I'm sorry. Whoop, whoop. And our galaxy recycles gas. Gas collapses into stars. The stars then expel that gas back into space through stellar wind, planetary nebulae, and supernovae. We call this recycling process the star-gas-star cycle. But the gas that comes out of stars doesn't have the same composition as the gas that went in. Recall that nuclear fusion builds heavier and heavier elements inside stars and during supernovae. So the gas stars expel, the gas the stars expel is enriched with heavy elements. Low-mass stars send their heavy elements into space as stellar wind, just solar wind with other stars, particularly in the red giant phase. Red giants lose a lot of their mass through stellar wind. Low-mass stars also send their heavy elements into space as planetary nebulae, like this one, when the star dies. High-mass stars also send their heavy elements into space in stellar winds, but also during supernovae, when they explode. And we call these heavy elements metals. I want to take a moment here to discuss this word, metal, because its meaning is changing from earlier in the semester. Sorry about that. Back when we were discussing the solar system, we said asteroids were made of rock and metal. We meant that in the everyday use of the word metal. Asteroids contain iron, nickel, and other dense materials that conduct electric currents, metals. But when discussing galaxies, the word metal means something completely different. In galactic astronomy, the word metal means any element that is heavier than helium. In other words, a metal is an element that is manufactured by stars, that is only manufactured by stars. Each generation of stars manufactures more and more metals. In other words, each generation of stars increases the metallicity of the galaxy. The two images at the upper left show the same supernova remnant, the Cygnus loop. The left image is what you'd see in a telescope with your eyes, visible light. The right image is a false color map of elements in the Cygnus loop. Sulfur is shown in red, hydrogen in green, and oxygen in blue. So to recap, the star-gas-star cycle. Gas collapses to form stars. Nuclear fusion in the stars makes new metals, then the stars expel those metals back into space through stellar wind, planetary nebulae, and supernova. The net result is that the galaxy gets more and more metallic with time. Recall that stars are born in clusters, and the most massive stars explode very quickly within a few 100,000 years. So when a cluster of stars has a bunch of supernovae, pow, 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 the collective shock wave from all those explosions can penetrate the outer edge of the disk, like water leaking out of a hole in a garden hose, spewing out of a hole in a garden hose. Those metals then rain back down onto the disk because of gravity. So by this mechanism, exploding stars can seed not only their own neighborhoods with metals, but faraway regions of the galaxy as well. A molecule, remember, is two or more atoms bound together by electricity. A star can manufacture heavy elements, but most molecules cannot form inside most stars because it's just too hot. Molecules can only form when it's relatively cool. So right after a supernova, the gas is really hot, but as the explosion expands, it cools off. It first becomes cool enough for electrons to bind to protons to become neutral atoms, mostly hydrogen gas. So the formation of atomic hydrogen is the first step in the cooling off process. Eventually, the explosion cools off even more, allowing molecules to form. Once a cloud of gas is cool enough for molecules, it is cool enough to collapse to form new stars, assuming it is also dense enough. Remember, hot gas has thermal pressure that resists gravitational collapse into stars. Only cool clouds, molecular clouds, can form new stars. This is the Orion Nebula in the constellation Orion. It contains a lot of molecular clouds, including molecular hydrogen and carbon monoxide, which is particularly easy to detect, and so astronomers use it as a tracer for other molecules and therefore star formation. If you see carbon monoxide, that's a clue. There may have recently been or may soon be star formation. The Orion Nebula also contains traces of water vapor. Don't ever let them tell you water is rare in space. It is not. Water is extremely common in vapor form. It's kind of hard to keep water liquid, so liquid water is kind of rare. It exists, of course, on the surface of the Earth because we have a glorious atmosphere to put pressure on it to keep it liquid. And it exists under the ice of certain moons, Europa, Ganymede, and Enceladus. The pressure there is provided by the weight of the ice above it. So liquid water is kind of rare, but water vapor is all over the place. Don't ever let them tell you water is rare in the universe. Anyone who says that patently is full of it. But that won't stop them from talking about science as though they know. The more massive a star, the hotter the star is, so the more ultraviolet light it emits. UV light is a destroyer of clouds. The hot, massive O-type stars and B-type stars and A-type stars erode the surrounding nebula like a psychedelic sculptor. Our eyes only see visible light, but our telescopes can see way beyond the visible spectrum. So let's look at the star-gas-star cycle in different wavelengths. Each of these strips is a panorama, a 360-degree image. The center of the image is the center of the galaxy, here and here, while the ends wrap around behind your head. The bottom image is what the Milky Way looks like in visible light. The galaxy has a lot of dust, which blocks out most of the starlight, so we can't see much of the galaxy in visible light. The top image, on the other hand, is the near-infrared. That is the infrared part of the infrared spectrum that is close to the visible spectrum, that is near the visible spectrum. Most space dust, turns out, is transparent to near-infrared light. So using near-infrared, we can see through the dust. Stars are also bright in the near-infrared, so near-infrared wavelengths tell us where in the galaxy most stars are located. Spoiler alert, they're in the disk. On the bottom here, we see X-rays, which maps extremely hot gas. There is X-ray emitting gas above and below the galactic disk, but also in small accretion disks around neutron stars and black holes that are stealing mass from binary companions. Up top here, we see a map of a specific radio wavelength, 21 centimeters. Atomic hydrogen gas emits 21 centimeter radiation. So looking for this wavelength tells us where in the galaxy there is atomic hydrogen. That is gas that is cool, but not necessarily as cool enough to have molecules, not necessarily cool enough for star formation. Carbon monoxide also emits specific wavelengths of radio waves. Carbon monoxide is a molecule that forms when clouds get cool enough to form new stars and had the added bonus of being easy to detect and very abundant. So astronomers use carbon monoxide as a tracer for new star formation. Where you see lots of carbon monoxide, there has either been or will soon be new stars. You, human, glow in the infrared because of your temperature. Dust in space does as well, particularly in the far infrared, that is, the region of the infrared spectrum that is far away from the visible spectrum. So far infrared light tells us where in the Milky Way dust is. Gamma rays are the most powerful photons that have yet been discovered. They tell us where nuclear reactions are happening in space, usually with energy left over from supernovae. Those are at the bottom, the gamma rays. So where do stars form in the Milky Way? You can tell that a nebula is forming new stars, partially because it's got molecules in it, but that's not the only clue. Also, some of these stars will be hot, young, and bright, and blue in color. So if there's hot, young, blue stars, there has to be ongoing star formation because hot, young, massive blue stars explode very quickly. They die when they're young. So if they're around, that's a clue that they are young, that these are young stars that you're looking at. Also, these hot, young, bright stars emit lots of ultraviolet light that ionizes the cloud around them. In other words, the ultraviolet light will strip the electrons right off the atoms. We call such clouds ionization nebulae. They emit a lot of red light as atoms recapture the electrons they've lost. Massive stars that emit mostly UV go supernova very quickly, so they're all young, which means if a nebula is ionized, it must have hot, young stars. In other words, it must be still forming stars. But not all of the nebula that glow are ionized. Some just glow because they scatter light from nearby stars. We call these clouds reflection nebulae. And reflection nebulae look like a reflection nebula looks blue for the same reason our sky does, because blue light scatters more easily than red light. This is the Horsehead Nebula. What kinds of nebulae do you see? The red is an ionization nebula, with the red light emitted as atoms recapture the electrons that they've lost. The blue down here is a reflection nebula, with blue light scattered by stars. Blue light emitted by stars, these stars right here, and then scattered by the gas in the nebula. So how do we know where stars form? Spectral lines of molecules, like carbon monoxide, are a clue. Also, ionization nebulae and the presence of hot, young, massive blue stars are a clue. All blue stars are young stars because blue stars die when they're still young. All of these clues are found in the disk of the galaxy, which tells us most ongoing star formation occurs in the disk. But not all regions of the disk are equal. The spiral arms, here and here. Spiral arms are regions of compressed gas, and gas must be compressed in order to collapse into stars. So most ongoing star formation happens inside the spiral arms as opposed to the regions between the arms. Not here. Here. Not here. Hot, luminous, massive blue stars are born in the spiral arms, and they usually die there because they die very quickly. Lower mass stars live long enough to flow out of the spiral arms and maintain an orbit around the galaxy. So to recap, our galaxy recycles gas. Whenever the interstellar medium is sufficiently cool and dense, mostly in the spiral arms, the clouds collapse to form stars. Stars manufacture new metals and expel those metals back into space, thus increasing the metallicity of the galaxy. So the disk has both young stars and old stars. But what about the halo? Well, it turns out the halo stars have a lot to tell us about galactic history because the halo stars are old, early generation stars. We know they're early generation because they have low metallicity. We also know that they are old because of their color. All the massive blue stars have died, leaving nothing but the long-lived red stars and the zombie corpses like white dwarfs. So halo stars, that is globular clusters, are what astronomers call old, red, dead. There is no new star formation happening. Now compare that to the disk stars, which astronomers say are hot, blue new. That is, the luminosity of the disk is dominated by luminous, massive, young blue stars. The disk stars are, on average, late generation stars. They are high metallicity stars. The gas in our sun was recycled from previous supernova explosions. What this tells us then is that the globular clusters formed first and then stopped forming. The disk, on the other hand, is still recycling its gas into new stars. So how did our galaxy form? Our understanding of it is vague because our best supercomputers do not have the computing power to model the full complexity of a galaxy. But our models do churn out artificial galaxies that look more or less like the galaxies we see in our telescopes, which means our models aren't wrong, but they are oversimplified. So we do have a vague understanding of galaxy formation, but the details are still being worked out. Keep that in mind as we discuss the formation of our galaxy. Galaxies form just like the solar system did, from a collapsing cloud of gas. That much at least we can verify with telescopes. To look far away is to look back in time, and we can look back to the time when galaxies were forming and see galaxies in the process of forming. However, those galaxies are really far in the past, which means they are really far away. So our images aren't very detailed, they're low resolution. Our data is about as vague as our computer models. Having said that, gravity pulls the densest parts of the cloud together first. So the densest parts of the protogalactic cloud collapsed first to form globular clusters. These clusters were so large and so dense, hundreds of thousands of stars all forming in close proximity. The most massive of them very quickly went supernova. Pow, 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 all together. In those early days, there were so many supernovae and globular clusters that were all going off like a fire in a fireworks stand, that the collective shock wave from these supernovae pushed the gas out from the center. And it takes gas to form new stars. So once the gas was stripped, star formation in globular clusters stopped. So globular clusters formed first, but then stopped forming. The remaining gas collapsed into a spinning disk, which formed stars more slowly than globular clusters. Yeah, supernovae have had a profound impact on the disk, but there haven't been enough supernovae clustered together in the disk to drive the gas out. So the disk continues to form new stars to this day. Now, here's a controversial part. Somehow, the disk forms spiral structure. There are several competing hypotheses about how spirals form, and as both telescopes and computer models get better and better, we'll have a better and better understanding of how spiral arms form. But for now, our understanding is vague. The evidence seems to suggest the disk further collapsed into clumps. It got clumpy. The most massive clump fell to the center to form the bulge. The less massive clumps were thrown outward. The inner part of the less massive clump orbited faster than the outer part, which stretched the clump then into a spiral arm. That's one of the hypotheses astronomers are now investigating. Come back in 5 years, the story may change as new evidence comes to light. Remember, science isn't perfect. It just gets better with time as we get new data. So we know our galaxy formed from a collapsing cloud of gas because that story is consistent with both telescope observation and computer models. We know that the halo stars, that is the globular clusters, formed first and then stopped forming because they have low metallicity and no young blue stars among them. The disk formed later and somehow evolved spiral arms. New stars continue to form in the disk. So, what's happening at the center of the Milky Way? In short, there is a monster there. What you're looking at is real data of stars orbiting an invisible object right there at the center of our Milky Way galaxy. We know it's very massive, otherwise stars wouldn't be able to orbit it. We know it's very compact, otherwise stars would crash into it. The image on the left shows the region inside of a couple hundred light years from the center of the Milky Way. It's an infrared image showing warmer regions. So the galactic central region is warmer than the surrounding regions. The image on the right is zoomed in somewhat and shows radio waves. Notice these arcs. That is a telltale sign of a magnetic field. So whatever very massive, very compact, invisible object lies at the heart of our Milky Way, it also has an intense magnetic field. Image on the left is zoomed in even farther. At this scale, the gas orbiting the central object forms a spiral structure like a hurricane or a flushing toilet. The image on the right is zoomed in even farther to about 1 light year. Now we see the actual stars orbiting the central object. The only object known to physics that fits the data we've collected is a black hole, an object in space with so much gravity it pulls space and time with it as it spins, and from its inside nothing can escape, not even light. The star's orbits tell us this black hole has the mass of 4 million suns. Astronomers call this black hole Sagittarius A star. That asterisk is pronounced star. Sagittarius A star. It's in the constellation Sagittarius, near the tail of Scorpio the Scorpion. The asterisk means its magnetic field emits radio waves, which is how it was discovered. So the name Sagittarius A star means the first radio source discovered in Sagittarius. But again, how do we know it's a black hole? Stars are orbiting an invisible object. Their orbits tell us the object's mass, 4 million solar masses. We know it's compact, otherwise stars would crash into it. The only physical object we know of that fits that data is a black hole. Now, don't touch your face. Sagittarius A star is not like the black holes we studied before. It is not, or may not be, the zombie corpse of a red supergiant star that exploded. Those black holes are only a few times the mass of our sun, a few solar masses, maybe a few dozen solar masses tops, and are scattered throughout the disk of the galaxy. But the black hole at the Galactic Center, Sagittarius A star, is a supermassive black hole, 4 million solar masses. And there are supermassive black holes at the centers of all the galaxies where we've been able to take a measurement, which suggests that all or nearly all galaxies have a supermassive black hole, a supermassive black hole like Sagittarius A star at the center, and we still don't know how they formed. They may have started out as a stellar mass black hole, the zombie corpses we learned about last time, and grown by eating gas, stars, or other black holes. That's possible. Or they may have been born by some other mechanism in the early universe shortly after the Big Bang. We don't know. To recap, at the center of our galaxy there are a few thousand stars orbiting a supermassive black hole, Sagittarius A star, 4 million times the mass of our sun. So, let's end now as we usually do with poetry. Say it with me. Gas in our galaxy is enriched and recycled in the star-gas-star cycle. Gas becomes stars, and stars release gas, and new metals are made with every pass. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. Here is homework 9, which is posted to Blackboard and due next Tuesday, April 14th. Here's a summary slide. There's no classwork today, and there will not be a retest for exam 3. Sorry. See you next week.